Section: Introduction. In this study, we present a new method to improve the performance of large pre-trained language models without the need for extensive fine-tuning or access to the model's internal weights. This method, which we call proxy-tuning, involves using a smaller, more easily tuned language model to guide the larger model's predictions. Large language models, while powerful, often require additional fine-tuning to perform specific tasks or operate within certain domains. However, this fine-tuning process can be resource-intensive and sometimes impossible if the model's weights are kept private. Our solution to this problem is a lightweight algorithm that can be applied during the decoding phase, without needing to access the model's internal weights. In our approach, we first tune a smaller language model, which we refer to as the expert. We then compare the predictions of this expert with its untuned version, which we call the anti-expert. This comparison is used to guide the larger base model. Our method involves shifting the base model's original predictions in the direction of the difference that results from tuning the smaller model. We tested this approach by tuning smaller models and using them to guide larger pre-trained models. Our goal was to achieve the performance of heavily tuned large models by only tuning smaller ones. We found that our proxy-tuning method was able to close a significant portion of the performance gap between the base model and its directly tuned version. In some cases, proxy-tuning even surpassed the performance of direct instruction tuning, suggesting that it may preserve more learned knowledge than directly updating the weights. We also applied proxy-tuning for domain adaptation, using it to adapt pre-trained models to code. This resulted in a significant improvement on coding benchmarks. Additionally, we used proxy-tuning for task-specific fine-tuning for question answering in math problems, which led to substantial improvements over the untuned model. Our analysis showed that proxy-tuning has the largest influence in promoting reasoning and stylistic tokens. For example, in math problems, proxy-tuning contributed more to formulating the left-hand side of intermediate equations, which represents reasoning steps, than deducing the right-hand side, where there is one correct answer. One of the advantages of proxy-tuning is that it doesn't require tuning any hyperparameters. However, if desired, one can be introduced to the ensemble, allowing users to control the amount of guidance exerted at runtime. In conclusion, proxy-tuning offers a promising method for efficiently and effectively customizing large pre-trained language models. It also provides a way for users to customize proprietary language models when the output logits are provided, even when weights are not, allowing organizations to protect their competitive advantage while satisfying user needs for adaptation. In terms of the method, suppose we have a large pre-trained model that we want to tune. We assume that we can access the output logits for the entire vocabulary. We also assume that there is a smaller pre-trained model that we can tune directly. Proxy-tuning works by adding a logit offset for every token, determined by the difference between logits from the untuned and tuned smaller model. The goal of proxy-tuning is to close the gap between the base model and its directly tuned version, without actually modifying the parameters of the base model. Section Summary. In this paper, the authors introduce a lightweight decoding-time algorithm called proxy-tuning, which allows for efficient customization of large pre-trained language models, LMs, without accessing their internal weights. By tuning a smaller LM and contrasting its predictions with the untuned version, proxy-tuning guides the larger base model to achieve similar performance as heavily tuned models. The method is demonstrated to be effective for instruction following, domain adaptation, and task fine-tuning, and it also influences the token-level probability distribution to promote reasoning and stylistic tokens. Section: Instruction Tuning Experiments. We're going to discuss our experiments on instruction tuning. Our goal was to see if we could use proxy-tuning to fine-tune a model during the decoding process. We used the Llama 2 model family, which includes base models that are pre-trained on text, and chat models that are further refined for dialogue through additional supervised instruction tuning and reinforcement learning from human feedback. Both base and chat models come in three sizes: 7 billion, 13 billion, and 70 billion parameters. We used the 7 billion parameter chat model as the expert and the 7 billion parameter base model as the anti-expert, and we adjusted the 13 billion and 70 billion parameter base models. We tested our models on 4 datasets, following the evaluation setup of Tulu 1 and 2 where possible. The first dataset, GSM, consists of arithmetic word problems with numerical answers. The second, Alpaca Farm, contains open-ended instructions, and we evaluated the model based on how well its responses performed against those from Text DaVinci 003, as judged by GPT-4. The third dataset, Toxygen, prompts models with hateful statements about a demographic group. The correct response is to not generate more hateful text. The final dataset, Truthful QA, contains often misleading questions, which we evaluated in 2 settings: multiple choice and open-ended question answering. Our results showed that for Alpaca Farm and GSM, the base models had difficulty addressing the question. However, Proxy-tuning the 70 billion parameter base model significantly improved performance. For Toxygen, decoding directly from the base models resulted in toxic responses 67 to 70% of the time, while Proxy-tuning reduced toxicity to 0% at both the 13 billion and 70 billion parameter scales. On Truthfulca's open-ended setting, Proxy-tuning actually outperformed the chat models at both the 13 billion and 70 billion parameter scales. We also measured the gap closed between each base model and its directly tuned chat version. On average, Proxy-tuning closed 91.1% of the gap at the 13 billion parameter scale, and 88.1% at the 70 billion parameter scale. Furthermore, Proxy-tuning a larger model outperformed the small tuned expert in all scenarios except for a 0.1% difference on Toxygen. This shows that Proxy-tuning is a highly effective alternative to directly instruction tuning large models. In the next section, we studied Proxy-tuning on code, due to the availability of relevant downstream tasks and off-the-shelf code models based on LLAMA2. We used CODELLAMA7B Python as the expert, which was initialized using Llama 2 to 7B, then further trained on general code and finally specialized on Python code. For simplicity, we'll refer to CODELLAMA7B Python as 7B code for the rest of this section. These experiments tested Proxy-tuning in a common practical setting where a language model is further pre-trained to fit a domain of interest, such as code, medicine, scientific text, or non-English languages. Section Summary. The authors first evaluate the application of Proxy-tuning to tune a model at decoding time using the Llama 2 family of models. They use different datasets to evaluate the performance of the models, such as arithmetic word problems, open-ended instructions, hateful statements, and misleading questions. The results show that Proxy-tuning improves the performance of the models in terms of win rate, accuracy, and truthfulness, suggesting that it is an effective alternative to directly instruction tuning large models. Additionally, the authors also study Proxy-tuning on code using off-the-shelf code models based on LLAMA2. Section: Datasets. We've tested our models on 2 benchmarks: Codex eval, which requires the model to write a Python function based on a given function signature and description, and DS1000, which includes Python programming problems from Stack Overflow. The accuracy of the generated code is automatically checked using test cases. We use a metric called pass at 10 to measure the likelihood that at least 1 out of 10 solutions for a problem is correct. This is calculated by sampling 20 generations per example with a temperature setting of 0.8. Our results show that pre-training models on code significantly improves their performance on coding tasks. For instance, at 13 billion parameters, we saw a 32.0% improvement on Codex eval and a 16.6% improvement on DS1000. At 70 billion parameters, the improvement was 8.6% and 6.7% respectively. However, we found that simply increasing the size of the model doesn't necessarily lead to better performance. We believe this is because once a model has been fine-tuned for a specific domain, generic pre-training at a larger scale doesn't add much. We also conducted fine-tuning experiments on specific tasks, including question answering, using the Trivia QA dataset, and math word problems, using the GSM dataset. For each task, we fine-tuned our model on the training set to create a task expert. We then compared the performance of the task expert with the base model. For the question answering task, we trained our models on 88,000 training examples from the Trivia QA dataset to predict the answer to a given question. We evaluated the models based on the exact match accuracy of the prediction against the reference answer. For the math word problems task, we used the GSM dataset, which contains 7,500 training examples. We trained our models to predict the original answer passage from the dataset. These answer passages are step-by-step solutions with specific formatting styles. Our results show that fine-tuning large models with a small, task-specific expert significantly improves performance. For instance, fine-tuning a 13 billion parameter model improved performance by 17.9% on Trivia QA and 35.3% on GSM. For a 70 billion parameter model, the improvement was 16.8% and 44.7%. This suggests that the method successfully combines the benefits of larger pre-training scale and task-specific tuning. Finally, we analyzed how fine-tuning operates at the token level and whether the strength of tuning can be controlled via a new hyperparameter. Section summary. The authors evaluate their models on two datasets: Codex Eval, which requires models to generate Python functions based on function signatures and descriptions, and DS1000, which consists of Python programming problems from Stack Overflow. The functional correctness of the generated code is automatically evaluated through test cases, and the authors report the pass at 1-0 metric, which measures the likelihood of at least one of 10 sampled solutions being correct. Proxy-tuning pre-trained models on code leads to significant improvements on both benchmarks, with larger models not necessarily outperforming smaller models that have been specifically tuned for a particular domain. Additionally, the authors experiment with proxy-tuning models on specific tasks, such as question answering and math word problems, and find that proxy-tuning large models with a small, task-specific expert greatly improves performance. Proxy-tuning a larger base model is substantially better for both tasks, indicating that the method successfully leverages the benefits of larger pre-training scale and task-specific tuning. Section. What kinds of tokens are most influenced by proxy-tuning? We're interested in understanding which types of tokens are most affected by proxy-tuning. To do this, we compare the next token logit distribution at each time step from both the 13B base model and its proxy-tuned version, and convert each into a probability distribution. We then look at the difference in probabilities assigned to the top token chosen by the proxy-tuned model. For the GSM, we specifically look at tokens on the left-hand side of intermediate equations, which require correct reasoning, and those on the right-hand side, which have a single correct answer. We parse all intermediate equations as sequences of math symbols containing the equal sign, and compare tokens to its left and right. We find that the difference in probabilities is 0.130 on average for left-hand side tokens, and 0.056 for right-hand side tokens, a statistically significant difference. This suggests that proxy tuning, which in this case represents the effect of instruction tuning, contributes more to formulating reasoning steps than to generating factual statements. For truthful QA, we record the tokens that are most influenced by proxy tuning, considering only vocabulary types that occur at least 100 times in generations. We show the 12 types whose probability increased the most from Llama 2 to 13B to its proxy-tuned version, along with the 4 grams that they most commonly appear in as an example context. These types are clearly contributing to stylistic changes, pushing back on the assumptions of the question, pointing out common misconceptions, refraining from answering, and acknowledging the complexity of the issue. Overall, these findings are consistent with the hypothesis that instruction tuning mainly influences reasoning and style, rather than increasing the model's knowledge. Next, we explore the impact of introducing a hyperparameter to the proxy-tuning formula to control the amount of modification. Intuitively, a larger hyperparameter magnifies the contrast between the expert and anti-expert, whereas a smaller one leads to more similar predictions to the original base model. For truthfulness, increasing the hyperparameter leads to consistent gains, potentially because instruction tuning improves a model's commitment to factuality in the face of misleading questions. In contrast, the informativeness peaks at a certain value. Perhaps because while some instruction tuning helps models address the question, excessive tuning increases the tendency to decline to answer. Overall, the smooth trade-off indicates that the hyperparameter can be adjusted by a user depending on their. Today, large pre-trained models form the basis of any kind of adaptation, whether for tasks, domains, or general-purpose dialogue. Moreover, scaling up the size of these models is a reliable recipe for further improvement. Thus, efficiently tuning ever larger models has become a pressing challenge, leading to a large body of work on efficient fine-tuning, commonly through updating a small number of parameters. Nonetheless, these methods require white box model access, which is unavailable for many of today's advanced models. In this context, tuning language models at decoding time represents a new approach for efficient fine-tuning. Our work shares a similar vision with contemporary work, which applies the same DEXPERTS equation as operationalized in our section. However, they mainly view the equation as a tool for analyzing the contribution of scaling up pre-training versus scaling up instruction tuning, and do not measure its effectiveness on existing benchmarks. In contrast, our work demonstrates the empirical strength of proxy tuning, as well as its generality beyond instruction tuning alone. Recently, others also combine the probability distributions from a small tuned model and a large pre-trained model, but through a learned combination function which requires additional data and training. For instruction following specifically, a curated prompt at inference time can elicit generations that are surprisingly competitive with instruction tuning. However, these prompts tend to be quite long, introducing an inference time computational burden and restricting the length of generations from models with limited context windows. Section Summary. The study investigates the influence of proxy tuning on different types of tokens in language models. For the GSM task, tokens on the left-hand side, LHS, of intermediate equations are more heavily influenced by proxy tuning, indicating its contribution to reasoning. In truthful QA, tokens that occur frequently in generations are analyzed, revealing that proxy tuning mainly affects stylistic changes in reasoning rather than increasing the model's knowledge. Additionally, introducing a hyperparameter in the proxy tuning formula allows for more control over the amount of modification, with larger values emphasizing the contrast between expert and anti-expert predictions. Section. Controllable generation. Controllable generation. A vast amount of research has been conducted in the field of controllable generation. This differs from tuning during the decoding phase as it focuses on managing specific attributes of the generated continuations, typically non-toxicity and positive sentiment. Various methods have been developed in this area that work on output logits. However, these methods differ from our work in their objectives. Moreover, many of these methods require the user to adjust additional parameters, such as a model with control codes or a head on top of the language model. On the other hand, proxy tuning enables users to utilize the wide array of small tuned models available online, combining them directly without any additional training. Logit arithmetic. Our research is based on the work of DEXPERTS, which introduced equation 1 and showed the effectiveness of combining output logits from multiple language models. This concept was also briefly touched upon in previous research. There has been an increasing number of studies that perform arithmetic on multiple logit distributions to improve text generation. These include contrasting the logits of a large and a small model, logits from different layers of a model, and logits from the same model given different inputs. We believe there is still more to discover in this area, such as ways to combine a large set of experts and non-experts, and dynamically adjusting the strength of steering, through a parameter similar to 2 divided by 2 in the alpha analysis section, at each time step.